So carbon is not created or destroyed here on planet Earth. Any exchanges that carbon has with outer space and Earth are negligible. That being said, carbon does very constantly exchange from one sphere of the Earth or from one system of the Earth to another. For example, what I just did right there was part of the biosphere, part of life, exhaled carbon dioxide into the atmosphere. That is a carbon exchange. That being said, the different components of Earth's system all have different roles that they play in the carbon cycle. So that being said, let's talk a little bit about the different Earth systems. So there are 5 different components of the Earth system, and we refer to these as spheres. The 5 spheres of the Earth. These are the 5 main components, the 5 main groups of the Earth system. So our Earth is made up of a conglomeration of these 5 things. And the 5 things are called the atmosphere. That is Earth's air. That's where our weather is. That's where rain comes from. When you feel the wind, that's happening in the atmosphere. That is Earth's air. That is my favorite sphere because that's the sphere that I geek out about. Then there's the geosphere, oftentimes also referred to as the lithosphere. Though if you're a geologist, they'll say, no, lithosphere is just the very top layer. But that's Earth's land. That's the solid Earth. So crust, mantle, outer core, inner core, land, that is the geosphere, or oftentimes referred to as the lithosphere. Then there's the biosphere. You and I, and every living thing on Earth is a part of the biosphere. So plants, animals, bacteria, they are all components of the biosphere. Then there's our water, our oceans, our rivers, our lakes, our streams. All of Earth's water is a part of the hydrosphere. However, there's one additional component to the hydrosphere that is so important that it actually gets its own designation as well, what is referred to as the cryosphere. That is Earth's ice. So that are the glaciers on the top of mountains such as Mount Shasta or Mount Everest. That represents the icebergs floating around in the Arctic or in the Atlantic Ocean waiting to sink another Titanic. That refers to ice caps on continents like Greenland, all of the ice on Antarctica. That is the cryosphere. And each one of these components, each one of these systems actually does store and exchange carbon with other systems. Now, that being said, each of these spheres plays an important role in the carbon cycle. Now, with that being said, there are actually 3 main roles that can be played by one of these 5 spheres. And in fact, these spheres can actually play multiple roles. But let me ask you right now, think of something that puts carbon into the atmosphere. You probably thought about us exhaling air. Or maybe you thought about burning of fossil fuels, driving around in a car, emitting greenhouse gases. Okay, now think about something that takes carbon away from the atmosphere, that takes carbon dioxide. I keep using those 2 terms interchangeably, but that removes carbon dioxide from the atmosphere. You probably thought of plants, maybe phytoplankton, maybe the ocean. You may have thought of something else. Those are usually the main ones. And then think about the atmosphere itself. The atmosphere doesn't give carbon and it doesn't take carbon away. Instead, it holds on to carbon. Well, what I have just mentioned are the 3 key roles in the carbon cycle. Things that add carbon to the atmosphere, things that take carbon away, and things that hold on to carbon. The things that hold on to carbon are present in all of these different spheres of the earth. The ocean holds on to carbon. Life, we are carbon-based life forms. We're basically giant walking, living, breathing lumps of carbon. Earth's ice actually has carbon trapped inside of it. Earth's lithosphere, diamonds are oftentimes found in the lithosphere. Earth's oceans, as I mentioned earlier, a lot of carbon is trapped in the ocean. So each one of these things actually holds on to carbon. And we call those things carbon reservoirs. A carbon reservoir is something that holds on to, stores carbon for a prolonged period of time. So the atmosphere is a carbon reservoir. Your bodies are a carbon reservoir. On the other hand, when you breathe out, that's what's called respiration. That is a carbon source. That is something that adds carbon to a reservoir. So if the atmosphere is our reservoir, you breathing out carbon dioxide, you have just added carbon dioxide to the atmosphere. That is a source. Now, before you hold your breath and think that you're lowering your carbon footprint, the good news is that on the other end, there are also a lot of processes that remove that carbon, such as the plants that are around you. If you look outside and you see green grass on the ground, that is actually something that takes carbon away from the atmosphere. That is what is referred to as a carbon sink. Photosynthesis, the act of converting carbon dioxide, water, and sunlight into sugar and oxygen, that is photosynthesis. That is a carbon sink. That is something that takes carbon away from the atmosphere. So that being said, carbon reservoirs hold on to carbon. Carbon sources put carbon into the reservoir. Carbon sinks take carbon out of the reservoir. But these reservoirs are actually very, very important. And one of the things that we as humans have actually done is we have actually disturbed some important carbon reservoirs. That's one of the reasons why we have effed up our carbon cycle. Just a few important carbon reservoirs. The atmosphere is an important carbon reservoir. Buried organic material, that dead stuff that we refer to as fossil fuels, mostly carbon, that is an important reservoir. Permafrost. So ice, stuff that is like permanently frozen. There's a lot of methane that is trapped in there from bacterial decomposition. As that stuff melts, a lot of that methane burps out. And then our oceans hold on to a lot of carbon as well. Now, that being said, you may feel like a deer in the headlights with the next image I'm about to show you, but hold on, I'm going to walk you through it real quickly. So this image right here shows a bunch of different exchanges between different components of the Earth system. And then wherever you see parentheses, these primarily refer to what's actually in the reservoir itself. So our atmosphere has approximately 800 gigatons of carbon in it. That has actually gone up over time because of additional fossil fuel burning and additional carbon emissions. Biomass, plant life, has about 550 gigatons of carbon in it. Soils have about 2,300 gigatons. Dead organic material, that fossil fuel stuff, has about 10,000. The ocean near the surface has about 1,000. The deep ocean has around 37,000. These are overly simplified numbers. All of these yellow numbers are natural carbon exchanges. So 90 gigatons of carbon are added to the ocean, and 90 gigatons are removed from the ocean. 120 gigatons are added to life via photosynthesis. 60 of them are respired back out. The other 60 go down into our soil and then are decomposed by microbial life, by bacteria. And then there are these red numbers. These red numbers actually represent human carbon dioxide emissions. For every 9 gigaton you emit, 3 of them are taken back out via photosynthesis. 2 are taken back out via absorption into the ocean. And so now there's actually more being added to our ocean than taken out. And all of this eventually makes its way throughout the rest of the Earth system, sometimes with negative consequences such as ocean acidification. But if you crunch the numbers, 9 gigatons are added by humans. 3 are removed via photosynthesis. 2 are removed via exchanges with the ocean. What about the remaining 4? So 5 of these gigatons are removed by natural processes, but the other 4 aren't. And so that means on an annual basis, and these are average numbers, on an annual basis, we are adding about 4 net gigatons of carbon dioxide into our atmosphere. What that means is every single year, we are adding an additional 4 gigatons, and then an additional 4 gigatons, and then an additional 4 gigatons. And that adds up really, really quickly. In fact, it adds up so quickly. That's one of the reasons why the 800 for our atmosphere was a little bit different than the 750 that we saw on a table earlier in this module. Because in just even a few short years, so much additional carbon has been added to our atmosphere that natural processes haven't been able to keep up with. That the amount of carbon, that the total amount of carbon in our atmosphere is going up, going up, going up, and going up. The real take-home message that I want you to get, though, is that of the 9 gigatons that we pump into our atmosphere, only 55% of it is actually removed. So that's 5 nines, 55% approximately. Only about 55% of it is actually removed via natural processes. The remaining 45% stays in the atmosphere, increasing carbon dioxide concentrations and therefore adding to Earth's greenhouse effect. That is why that's so concerning. Now, that being said, there is some removal due to natural processes. 5 of the 9 gigatons that we're pumping in are removed by natural processes. Why can't they do all 9? Well, it all has to do with timescales. We're going to talk about that in the next few videos.